All right, Unit 7 review. So scale factors. There's a bunch of stuff in this one, right? We did scale factors. We went through lines of symmetry, order of rotation, angle of rotation, and then just kind of in general, just transformations, rotations, and reflections, like on a Cartesian plane like this. So I'm going to go through the assumption that everybody kind of remembers a bit of this. So it's just going to be a review. I won't be like explaining it from step one again. But going way back, scale factors. What do we mean by scale factors here? Well, scale factors is just really how many times bigger something is, or really, how many times smaller is something. So in general, right, if I said that something is twice as big as something else, right? So if I had like a line here that was 2, this is going to seem very simple. If I had a line that was like 2 long or something, right? And I said something was twice as big. Well, how big is it? Well, that would be a line that was 4 long, right? So the scale factor here, if I said it was twice as big, is really just 2, right? So you'd be saying, yeah, so that's 2 times my scale factor of 2 is equal to 4. And I know this sounds like ridiculously simple right now, but kids have a hard time with it sometimes. But so if I had something like this now, let's say that I had something that was, a box that had a side length of 4, and I said that another box was 3 times bigger, or that had a scale factor of 3, I guess we would say. Well, that would just mean that every side length on the box was 3 times bigger. So here, if this was a box and that was 2, right? And I said that the scale factor was 3. That means everything would be multiplied by 3. So it'd be 4 times 3 would be 12, and 2 times 3 would be 6, right? So everything is that many times bigger. Now, just remembering here that if we go the other way, so if something has a scale factor of, well, here, I'll give you an example. So if, let's say now we have a box again. Doesn't need to be a box, it could be a triangle or any polygon. So now let's say that we have something that was, so this is a length of 4 and that's a length of 2. And now I said that let's make a scale image that is half the size. Well, what that means is that my scale factor is going to be a half, or 0.5. Now notice that these numbers, like a half or 0.5, that they are bigger than 0, but they're less than 1, right? So if you multiply, so if I go 4 times 0.5, or 4 times a half, that's getting smaller, right? It's actually, well, it's 50% the size. So that's going to make our object smaller, right? So if you get a scale factor of a decimal between 0 and 1, or a fraction that ends up being between 0 and 1, then you're making the thing smaller and you're making it half the size. So this would be 2, right? So in this case, we'd be making a smaller little box that was 2, right? 4 times a half is 2, and then 2 times a half is 1. So you're making it smaller in that way, right? So yeah, that's pretty much it. That's the gist. Another way we can write this, though, is quite often we use the symbol K for scale factor, and you'd say K is equal to the model over the actual. So the model over the actual. So if I wanted to figure out what the scale factor was, so let's say that this is our model, right? The big one is our model, and this was our original diagram. And I wanted to figure out what's the scale factor of, well, turning the original into the model. Well, that's as simple as just saying, okay, well, K is equal to, and then I can pick any side length, right? So I'm going to pick, well, they're all the same because it's a box, but so we'll say the model is 7, and then the actual is 2. So there you go. The scale factor is 7 over 2. You could divide that, right? We can go 7 divided by 2. So we get a scale factor of 3.5, right? So what that really means is that if I take any side length on the original, so like 2, and I multiply it by 3.5, or 7 over 2, I'm going to get that one. Okay? And it would work the same way if we went from the original and said this was our model, which would be a reduction. So in that case, you'd say K is equal to, and then the model is 1, and the original was 2, right? Model over actual. So there you go. There's your scale factor of 1/2. And again, so I can multiply 2 by 1/2 to get that 1, okay? All right, so that's the idea with our scale factor type of questions. So here, I'll give an example here now. So let's do one like this. So let's say we had a triangle that did something like that. And these are similar triangles, even though I didn't really make them very straight. So let's say that this length here was 10, and this length here, let's say, is 8. And then we know that this length is 4. Okay? And maybe the question is saying, what's the length from like here to here? All right, so how can we figure this out? Well, can you guys see that the similar sides on these two triangles would be the 4 and the 8, and then the 10 and the X, right? Those are the ones that are like, that are the similar parts of these triangles, right? So really what I had to do here is I had to go 8 times something, some scale factor to get 4, right? So 8 times something to get 4. Well, I'm gonna have to do that same thing here. I'm gonna have to go 10 times that same scale factor to get X. Maybe some of you guys have done this in your head already, but we'll spell it out here. So let's figure out our scale factor that we're using to go from this triangle to this triangle. So we're gonna say, okay, well, K is equal to the model over the actual. So to figure out our scale factor, we'll say K is equal to, now the model was 4, right? That we're comparing this side to this side, just so we can get our scale factor, because those are the numbers that we have. So we'll say 4 over 8. So that's the same thing, just simplifying that fraction as 1 over 2, or 0.5, it wouldn't matter. Okay, so there's my scale factor. I'm good to go. I should be able to just multiply this 10 now by our scale factor to get X. So we can say 10 times, maybe I won't use times because I used X up there. They look similar. So 10 times 0.5 is equal to 5. Okay, so this would have, so X would have to be equal to 5. Now I made it really simple numbers, but it would be the same thing if this was, you know, maybe this was 6 or something, so it wouldn't work out quite so nice, right? Or 7 or anything else. So it might be a decimal that you're like a different decimal that you're multiplying by there instead of a half, right? That was 4. Okay. All right. So that's the idea. Yeah. They are a little bit tougher on your guys. This is formative there, but that's the general idea for those ones. So, okay. Lines of symmetry. All right. So lines of symmetry are really just where you can make a line that's going to cut the thing in half, right? Where you could like fold it over. Like if you imagine it was a piece of paper, right? If I had this line going straight down the middle, I could fold this side over and it would completely match the other side. So it's called a line of symmetry, because if something's symmetric, it's the same on the right side as it is on the left side, right? So there you go. And with like a box like this though, you can get multiple lines of symmetry, because if it really was a box or a square, then you could also fold it across from corner to corner, right? And you could flip this side over from there to there. So that's symmetric on each side. And really every one of these lines would be symmetric on either side of it, right? So that'd be a line of symmetry. The star, I don't know what happened here, but the lines disappeared. There would also be other lines of symmetry on the star like that, right? So there'd be one there. You could have one there. You could have one there. So those would also be lines of symmetry, right? On this. So if the question said how many lines of symmetry are there, we'll count the lines at this point. So you've got 1, 2, 3, 4 lines of symmetry on that guy. Just wait. 1, 2, 3, 4. Oh, I missed one. Yeah, that didn't seem right. 5. Okay, there you go. So 5 lines of symmetry on that one. 3 lines of symmetry on this one. And then this one, right, there's no other way to cut this. This only has 1 line of symmetry. I can't make another one there because that wouldn't fold over nicely, right? All right, so that's pretty much it for your lines of symmetry. Order of rotation. So order of rotation is saying how many times can you turn this thing where you get the exact same picture of itself, right? So like in this case, if I can imagine flipping this thing this way, right, from like there to there and there and around, then if I rotate this thing around 180 degrees, well, actually, I shouldn't even say that yet. We'll get to that below. But if I can rotate this thing 2 times and get itself back, right? So if I rotate this thing so like this corner of this box could end up here, right? So that would be 1, and then back again to get to that point again. So it can actually rotate 2 times. So there's an order of rotation of 2 where it looks exactly the same. Okay, a triangle, if I start off with this corner, right, then I can move this up and to the top, and it's going to look exactly the same. And you can do that 3 times before you get, 1 full circle all the way around, right? So that's an order of rotation of 3, order of rotation of 4, right? Similarly, and then order of rotation of 5. It's like little ka-chunk. This one goes up here and goes ka-chunk, goes up to the top. That's kind of how I picture it in my mind anyway. I don't know if that makes sense to you. Okay, and you can see on this one, right, that this wouldn't have any, because if I flip this corner up to the top, it's not going to look exactly the same. It has to look exactly the same going around, right? So this one will look exactly the same 2 times around, 3 times, 4, and 5. Okay, order of rotation. So looking at this shape here, we can see that this one would look exactly the same 2 times around. So it has order of rotation of 2. So really, to figure out the angle of rotation to do that, it's going to be the angle of a circle, so 360 degrees divided by 2, so 180 degrees, which makes sense. I would have to flip this thing around 180 degrees to make it look identical for that first order of rotation, right? So one like this, right, if I want to figure out what the order of rotation of this one was, well, order of rotation of 3, so it would just be 360 divided by, well, order of rotation of 3. So 120 degrees, right? Okay, moving on. Transformations, rotations, and reflections. So I figured just the best way to do this, I'm just going to give you an example and we'll go through this one together. So here's a typical type of a question. So they'll say, we need to perform transformations of 270 degrees clockwise rotation about the vertex L, and then a translation of 3 units up, 6 units to the right. So first off, let's talk about some vocab here. 270 degrees clockwise. So I know kids don't use analog clocks very often anymore, but a clock, right, if you've got your hands, going this way, clockwise is the direction that the clock turns. So it would be going that way, right? That's clockwise, going that way around, and then counterclockwise would be going that way. So I'm always surprised how many kids have never seen that before, but okay, so now you know. It's being rotated about the vertex L. So vertex is really just where something comes to a point. So it's like that's a vertex, and that's a vertex. But they've said around vertex L. So what that means is that we're gonna like put our finger on L, and then this shape itself is going to be rotated, and it's clockwise, so it's gonna be rotating that way, right? So put your finger on that and then move the rest of it around. And we're moving at 270 degrees. So 270 degrees would be, I don't know if any of you guys snowboard or like ski or any other skateboard or whatever. If you do a 180, then that's turning yourself completely from one end to the other, right? That's 180 degrees. So here, I'll draw it in the same way that we're doing this one. So, so 180 degrees would be from here to there, right? 180. 360 be all the way around. So 270 would actually just be around to there again, right? Just like 3/4 of the way around is what 270 is. Okay, so that's our first step. And then we're going to translate the thing 3 units up and 6 units right. So the rotation, I think, is the hard part of this. So let's do that first. And then we're going to draw a little triangle. And then we're going to move that triangle to where it needs to go. So in order to do this, what I'm going to do, I'm going to focus on this point right here. And then I'm going to figure out where to put this line, I think, right? So you can imagine, like I said, this thing goes around, there's 180, and then coming around again, there's 270. So really this back part of this triangle is going to be right there, right? That's going to be the new back part of that triangle. Okay. And then this, you can imagine the front of this triangle, right? This piece of it was traveling around as well. So now that part of it is going to be on the front there. And now once you get it kind of drawn, you can kind of see how that happened, right? So that would be my 270 rotation, would be down to that point. Okay, so now that I have that rotation figured out, now I just need to move the point, what did it say? Up, 3 units up, 6 units to the right. So 3 units up. So all I got to do is every one of these points, I'm just going to count up 3. So 1, 2, 3. So that's my new L. This point here, I'm going to move up 3. I made this awkward, so that's going to be there. And this one's going to move up 3, so that's going to be there. Okay, so if you wanted to, there's your new triangle at that stage of it. You know, delete or get rid of that just so it's not confusing. But now we're going to move it 6 units to the right. So every one of those points is going to go 1, 2, 3, 4, 5, 6. I'm looking at this one now. 1, 2, 3, 4, 5, 6, which makes sense. It's in a line. And then 1, 2, 3, 4, 5, 6. And there you go. There's our new triangle that's been rotated and then translated by those coordinates there. So now looking at this, it said, what are the ordered pairs of the vertexes? So what we can do here, you can see that from the beginning, right? That was my L point. So that's my new L point. And I'm going to say L prime with a little tick there, and then just say where it's at. So where am I at now? So I moved over 4 on the x-axis, so I'm going to be 4, and then I'm right on the I'm right on the x-axis, so my y value here is 0. Okay. Now the other one, so this k value, remember what we did? Like this was k down here after we reflected it, and then we moved it up and then moved it over. So this is k prime right there. So this point is over 4. So my x value is 4. And my y value is down 3. So -3. Okay. And then this is my j. So I'll say j prime. And that point is over 2. And then down -3. And there you go. All right. So let me double check. I think we kind of went through everything here. Yep, that should be it.